Have you ever blown up a balloon? If so, you might have stretched it before trying to blow it up. That's what I'm doing with these balloons for my friend's party, and it makes it much easier. But that does make me wonder, why does stretching balloons make them so much easier to blow up? Hi, I'm Annika, a second-year student studying creative technology and design at CU Boulder. And to understand why balloons are easier to blow up once they've been stretched, let's stretch our minds around a special kind of material and learn all about viscoelasticity. Everything in our world that we can physically interact with is made of materials. There are lots of kinds of materials: fabrics, plastics, liquids, metals, organic materials, and so on. Anytime we're making something, we have to decide what materials to use based on what that thing needs to do. And to make the decision easier, we divide materials into categories. Some of those categories are solids and fluids. Solids are materials that resist change in configuration or volume, meaning they maintain their shape. Fluids flow to take the shape of their container and include both liquids and gases. If you put a fluid in a bowl, it'll take the shape of the bowl, while a solid will hold its original shape. But there are certain materials that don't act exactly like solids or fluids. Some of these materials include elastic solids and viscous fluids. We have entire videos about both of these concepts that include a lot of information we'll build on today, so go watch those if you haven't. To quickly explain, elastic solids are solids that return to their original forms after being deformed. If you push on a piece of foam, it'll deform, and there'll be an indent of where you pushed. But eventually, it'll go back to its original shape. This is an elastic solid. Viscous fluids are fluids that react differently depending on how much force is applied to them. Some act more like a solid the harder you push, like oobleck, while others act more like a fluid the harder you push, like toothpaste. But what about something that's almost in between an elastic solid and a viscous fluid? Something like silly putty, that when you try to pull it, breaks like a solid, but will deform to the shape of its container when you leave it alone for long enough. Well, silly putty and materials like it are viscoelastic materials. Viscoelastic materials are materials that exhibit both viscous and elastic material responses, a material response being how a material responds to a force. We often categorize these further into polymers and biological materials. Polymers are materials composed of one type of molecule repeated in a chain. Things like plastic and rubber are polymers. Biological materials can sometimes have the structure of polymers, but are classified differently because they come from something living, such as skin or cartilage. Like I mentioned, the defining characteristic of viscoelastic materials is that they exhibit both viscous and elastic material responses. There are three main factors that affect how they react to forces: the rate at which a force is applied, how long a force is applied, and how many times the force is applied and removed. Let's look at each of these in detail. First, the rate at which a force is applied. Viscoelastic materials have strain rate dependence, meaning they react differently to forces depending on how fast or slowly those forces are applied. Let's think back to the silly putty. When we pull on the silly putty quickly, or apply a force at a fast rate, the silly putty acts like an elastic solid that's reached its ultimate tensile strength and breaks. However, if we were to pull on it slowly, it would stretch for seemingly ever like a highly viscous fluid. This reaction is common across most viscoelastic materials. When stressed slowly, they will act like viscous fluids, but when stressed quickly, they will act like elastic solids. We can see this effect quite clearly in the stress-strain diagram of a viscoelastic material. Let's draw two different lines, one based on straining a material at a fast rate, and the other based on straining the material at a slow rate. You'll notice that both lines have a curved region followed by a linear region. At the fast rate, the radius of curvature, which is the radius of the circle that best represents the curve, is smaller, and the linear region has a larger slope than the slow rate. The curved region represents the material's viscous response, while the linear region represents the material's elastic response. So, when stretching a viscoelastic material quickly, the material spends more time in the elastic region, while stretching slowly results in more time in the viscous region. Thus, stretching a viscoelastic material quickly results in it acting more like an elastic solid, while stretching it slowly results in it acting more like a viscous fluid. So, the rate at which you stretch a viscoelastic material affects how it responds. That's one of three. Now, let's look at how the length of time a viscoelastic material is stretched affects its response. Viscoelastic materials exhibit something called stress relaxation, which means that upon applying a constant displacement, the force the material experiences decreases over time. Generally, what this means is that the longer you strain a viscoelastic material, the easier it becomes to keep that material stretched. If you think about pulling a rubber band super tight, it's super hard to hold at first. Over time, though, it's like the rubber band gets used to being held tight, and it becomes easier to hold. Eventually, the rubber band, and all other viscoelastic materials, will reach a point of equilibrium, where the material is in a constant, steady state, and the force will stop decreasing. It'll stop getting easier to hold. We can see stress relaxation on a graph by mapping the stress a material experiences over time. As time goes on, the amount of stress the material experiences decreases, until eventually leveling out. That leveling out is the material reaching equilibrium. Another effect of time on viscoelastic materials is creep. Stress relaxation involves applying a constant displacement to a material. Creep, on the other hand, involves applying a constant amount of force to a material. As you pull with a consistent force on a rubber band, over time that rubber band will stretch farther. Then, when you release it, it quickly shrinks back down to not quite its original size, and then takes some time to return fully to its original configuration. In other words, a constant force results in an increase of displacement over time, and then, once the force is removed, takes time to recover back to a displacement of zero. The increase in displacement with force over time is considered creep. Let's graph this phenomenon by mapping strain versus time. The first linear part of this graph is the initial displacement from applying the force. As time goes on and the force remains constant, the strain continues to creep up until eventually leveling out. This leveling out, just like with stress relaxation, is from the material reaching equilibrium. Upon releasing the force, the displacement immediately drops the same amount as it initially increased, before taking time to return all the way back to a strain of zero. Through both stress relaxation and creep, the length of time a viscoelastic material is stretched affects how it responds. There's one more factor for us to look at: how many times a force is applied and removed. When you load a viscoelastic material, or apply a force to it, that material stores energy so it can later return to its original configuration. When you unload it, or release that force, the material uses up the energy to return to its original configuration. But hold on. Do you see that weird gap between the loading and unloading curves on this graph? That's a special feature of viscoelastic materials called hysteresis. Viscoelastic materials actually take more energy to load than to unload. When loading a viscoelastic material, a certain amount of energy is used for something other than the actual stretching of the material, like heat dissipation or molecular rearrangement within the material. Thus, while the material still has enough energy to return to its original configuration, it's actually taking less energy than loading did. And the difference in energy between loading and unloading, the energy that was lost, is called the hysteresis. As you repeatedly load and unload a viscoelastic material, the amount of energy lost in each cycle decreases until eventually the material has reached equilibrium, and there's almost no energy lost. Also, the amount of force it takes to displace the material decreases with each cycle. This process is called preconditioning. Also, notice how by the time we've reached equilibrium, our diagram has a much smaller radius of curvature than it started with. What we've essentially done is get rid of the viscous part of the material's response, so that only the elastic part remains, while also making it easier to displace the material. So, if an engineer wanted to use a viscoelastic material for something that required a more consistent reaction to forces, they could precondition that material so that it would act the same every time it reacted to forces. And now, finally, we know why balloons are easier to blow up once we've stretched them. Balloon latex is a viscoelastic material. So, when I repeatedly stretch a balloon, I'm preconditioning that balloon and making it easier to stretch. That way, it's as easy as it can be to blow up. We went through a lot. Let's review the main points one final time. Viscoelastic materials are materials that exhibit both viscous and elastic material responses. These materials have strain rate dependence, meaning that they react differently based on the rate at which a force is applied. Applying a force quickly usually results in a more elastic response, while applying a force slowly results in a more viscous response. These materials also experience stress relaxation, meaning that the longer they remain at a constant strain, the less stress is required to keep it at that strain. There's also creep, where applying a constant force to a viscoelastic material results in an increase in strain over time. Viscoelastic materials also experience hysteresis, where they take more energy to load than to unload. And the more that you precondition one of these materials, meaning the more you repeatedly load and unload it, the less force it takes to displace the material, and the less viscous the material acts. And just like that, we now know a lot about viscoelastic materials. And we know why stretching a balloon makes it so much easier to blow up. Speaking of balloons, I have a whole bunch more to blow up before this party is ready. Thanks for learning with me, and until I see you again, I hope you can find something in engineering to blow your mind. Check out the full lesson on Teach Engineering, then use what you learned in the associated activities, Creepy Silly Putty, and Preconditioning Balloons, Viscoelastic Biomedical Experiments.